Here is the most innocent-looking loop in programming. Result equals the empty string. For each line in the file, result equals result plus line. Read lines, glue them together. Every one of us has written this. Now feed it a real file. 10,000 lines? Instant. 100,000? A noticeable pause. 1,000,000 lines? About 100 megabytes of text. Minutes. Sometimes much longer. Count the steps the way the first lesson taught you. 1 append per line, in lines. Order in. The stopwatch says otherwise, and by the end of this lesson, you'll be able to put a number on how wrong that count is. The number is measured in terabytes. The structure responsible is the one we ended last time pointing at, the string, because a string is an array of bytes wearing a trench coat. Everything you've priced in the last 2 lessons, contiguous blocks, cache lines, grow and copy, all of it applies. But the coat hides one rule that changes the entire cost model. Let's pull it open. Underneath the coat, the picture is familiar. A pointer to a contiguous block of bytes, and a length stored right beside it. That's a Go string, a Java string, a Python string, a 2-word header over a block. So the prices you already know carry over. Indexing a byte, order 1, base plus offset. Scanning, sequential, cache-friendly, the prefetcher streams it. And asking for the length is order 1, because the length is a field. You read an integer that's already sitting there. That last one sounds too obvious to say out loud, except you've seen what happens without it. C does not store a length. A C string is just bytes ending in a 0, so finding the length means walking the bytes until you hit it. That's Sterling. That's what scanf called in the GTA story. 10 megabytes walked per token, 63,000 times. The stored length is that fix, institutionalized into every language designed since. So far, a string is just last lesson's machine. Now look at what's missing from the header. No capacity, no spare room, because there is no append. You cannot change a string. Not one character. In Python, Java, JavaScript, Go, C#, every operation that looks like it edits a string actually builds a new one. 5 language teams independently locked the same door. Why? Watch what would break. Take a Python dictionary and insert a value under the key Alice. The dict hashes the key, and the hash picks the bucket where the entry lives. Now suppose strings were mutable, and some other code holding a reference to that same key changed one character. Alice becomes Alice F. The entry doesn't move. It's still sitting in the bucket that Alice hashed to. Look up Alice F, you hash to a different bucket. Nothing there. Look up Alice, right bucket, but the stored key no longer matches. The entry still exists, and no key on earth can reach it. The dict is silently corrupted, and nothing ever threw an error. Freeze the string, and that whole failure mode is gone. Better, the hash can be computed once and cached inside the string. Lesson 12 caches that in. And the same freeze buys safe sharing. No defensive copies, no locks, one interned copy of a common string reused everywhere. Immutability is a bargain. The price is the rest of this lesson. Here's the bill. S plus T. Both inputs are frozen, so there is exactly one way to implement it. Allocate a fresh block, the length of S plus the length of T. Copy all of S in, copy all of T in. Every concatenation copies both of its inputs in full every time. Now replay the innocent loop with that price tag. Append 1, copy 1 line. Append 2, result already holds a line, so copy it plus the new one. By append number k, result holds k minus 1 lines, and you copy all of them again just to add one more. 1 plus 2 plus 3, all the way to n. That sum is about n squared over 2, the same parabola from lesson 1. Make it concrete. 1,000,000 lines, 100 bytes each. The finished file, 100 megabytes. The copying along the way adds up to about 50 terabytes of bytes moved. 50 terabytes of copying to build 100 megabytes. Even at memory bandwidth, that's the better part of an hour spent entirely on moving bytes. The loop looks order in because you counted appends. Each append secretly costs the current length. A hidden order in stacked n times order n squared. This trap is old enough to have a name. 2001, Joel Spolsky writes an essay called Back to Basics and tells a joke. Shlemiel gets a job painting the lines down the middle of a road. Day 1, he paints 300 yards. Day 2, 150. Day 3, 30. The boss demands an answer, and Shlemiel says, "I can't help it. Every day the paint can stays where I started, and every day I have to walk farther and farther back to dip the brush." Spolsky told it about concat, C's concatenation, which has it even worse than our loop. No stored length, remember? So before appending a single byte, Scrat must walk the destination just to find the end. But our loop is Shlemiel too, even with the length stored. It recopies the entire road every single day. Engineers genuinely call these Shlemiel the Painter algorithms, and once you know the name, you see them everywhere. The fixed-step growth from last lesson, GTA's duplicate scan. Anywhere work that's already done gets redone on every step. And the fix is always the same idea. Keep the paint can with you. You already built the paint can. Last lesson. A builder is a dynamic array of bytes. That's the entire secret. Go calls it strings.builder. Java, string builder. Python's idiom is to append the pieces to a list and call join at the end. Different costumes, same machine. Pointer, length, capacity, doubling on growth. Run the prices. Each append lands in spare capacity. Write, bump, order 1. The occasional doubling copies what's there, and last lesson proved all the doublings ever, summed, stay under 2n. At the end, one final order in conversion freezes the bytes into a real string. Total, order in. The 100 megabyte file costs a few hundred megabytes of movement instead of 50 terabytes, milliseconds instead of an hour. And join is even sharper. One pass to add up the lengths. Allocate the exact final size once. Then copy each piece into place. No doubling, no waste. That's pre-sizing from last lesson, applied automatically. If you drive a builder by hand and know the final size, say so. Grow in Go, ensure capacity in Java. Same verb, same reason. Now some honesty, because if you benchmark this yourself, 2 languages will appear to make a liar out of me. Run the plus equals loop in CPython, and it's often fine, linear even. CPython cheats. When the string on the left has a reference count of 1, nobody else can see it, so the interpreter quietly resizes it in place, mutating the immutable where no one can catch it. It's a beautiful trick and a terrible contract. Hold a second reference, and it evaporates. Run a different Python implementation, and it evaporates. The official docs still say, use join. JavaScript goes further. V8 often doesn't copy on plus at all. It builds a rope, a tiny node that just says left half, right half, and only flattens the tree when something needs the actual bytes. So plus equals in a loop in modern JavaScript is usually fine too. So why did I just teach you the quadratic? Because these are engine internals, not promises. The model is concatenation copies. When an engine saves you, it's a gift. Take the gift. Don't build on it. Write the builder, and you're fast in every language, every runtime, every version. Concatenation is the famous tool. It is not the only one. Slicing. Take a big string and ask for everything but the first character. In Python, that's a copy, n-1 bytes. Slice inside a loop, and you're Shlemiel again. Most languages copy on slice. The interesting case is the language that doesn't. A Go substring is a new header over the same bytes. No copy, order 1, last lesson's aliasing story, wearing the trench coat, fast and sharp. Pull a 10-byte token out of a 100 megabyte document, keep the token, and it pins the entire 100 megabytes. The garbage collector can't free a block while anything points into it. And Java's history here is delicious. Java substrings shared for 17 years, until 2012, Java 7, Update 6, when the JDK switched substring to copying, precisely because of the pinning bug. 2 languages, same trade, opposite answers, and you can now argue both sides. The quick ones to file away: comparing 2 strings, order in, walk until mismatch. Searching inside one, at least order in. Only the length is free. One last pocket in the trench coat. This whole lesson priced strings in bytes, and bytes are not characters. In UTF-8, an A is 1 byte, an E with an accent, 2, an emoji, 4, and a family emoji is several code points glued together. So the same string answers the length question 3 ways. The poop emoji. Length 1 in Python. Length 2 in JavaScript. Length 4 in Go. None of them is wrong, they count different units. And none counts what a user would call a character. Indexing by character means walking from the start. Order in, not order 1. And the bug is real. Truncate a username by slicing bytes, cut an emoji in half, ship garbage. For cost, think bytes. For text, cut only at boundaries a real Unicode library gives you. That closes the first module, the cost of everything. You can read a growth curve. You know what a step physically costs. You've built the machine under every list. And you've seen the costs strings hide under the coat. Next module, linear structures and their patterns. Starting with the structure this module kept tolling. The linked list finally gets its day in court. When they actually beat arrays, that's next.